The much-loved 555 timer chip is over 50 years old now, and it is still as popular as ever. There are many YouTube videos which have been made on using the 555 timer, and these are entertaining and informative and get to the point, skipping over important details. In this video, I'm going to take a deep dive into the theory and practice of the 555 timer. This will be the first of many videos I'll make on the 555 timer. In this video, I'll be looking at the 555 as an astable, and specifically we'll be exploring the mark to space ratio of the square wave output and whether we can get to a perfect one-to-one mark to space ratio. And then after that, we'll see if we can control the mark to space ratio any further. Now this is going to be a long and detailed video, unlike any you've seen on the 555 timer. There is a lot of experimentation involved and a lot of proving of the theory. This video has been shot and recorded over several days. The monotonous bits are sped up to save you a bit of time, and I'll slow down for explanations and details. Let's begin by setting some objectives and how we're going to proceed. So firstly, we'll look at the formulas for the mark to space ratio for the generated square wave output. Can we get a one-to-one mark to space ratio? Is there a simple way? Is it more complicated than that? How much precision is required? What are the practical values of R1, R2 and C that are optimal? Are there any limits before the circuit breaks down? And can we discover any new knowledge about the best resistor and capacitor values? So with the method, we'll build the circuit, which we'll do very shortly. Then we'll examine the 555 data sheet, and then we'll construct the hypothesis based on the formulas. And then we'll test this hypothesis by placing R and C values into the built circuit and take measurements. And then we'll draw some conclusions. The 555 astable circuit is straightforward to construct, beginning with pins 8 and 4 to positive and pin 1 to negative. Pin 2, the trigger pin, and pin 6, the threshold pin, are connected together. A timing capacitor connects from pins 6 and 2 down to ground. I'll get back to the timing resistors in a moment, but I just wanted to add a couple of colourful red and green 3mm LEDs ready to connect to the output pin, pin 3. The way I'm using these is green is going to represent the mark and red is going to represent the space. The green LED connects via a 1 kilo ohm resistor to the output of the 555. And the cathode of the green LED connects to ground. The anode of the red LED connects to the 9-volt power supply, and its cathode connects to a 1 kilo ohm resistor, which then connects to the output of the 555. So you can see the output of the circuit is quite symmetrical, with the two 1 kilo ohm resistors connected together and then to the output of the 555 with the blue wire. Now I'm connecting a 100 kilo ohm resistor from positive to pin 7. Next I have plucked a convenient 5 kilo ohm potentiometer or variable resistor, which I'll connect between pins 7 and 2. Lastly, a couple of wires to connect power to the circuit, and our initial build is complete. Now we can slow down to normal speed, turn on the power and see if the circuit works. As we power up the circuit, we can see the green LED appears to be continuously on, and the red LED is very dim. Adjusting the potentiometer appears to have little impact on the circuit's function. I had these kinds of teething troubles in my last video too. But this is no accident. The capacitor is small in value. It is a 330 nanofarad capacitor. Removing the blue wire from the output, pin 3, to the LEDs simply puts both LEDs in series with the power supply and makes them both have the same current flowing through them. So that does not account for the asymmetric light output from the two LEDs when they are connected to the output of the 555. Have you figured it out yet? The mark to space ratio of the square wave output from the 555 must be very high, but the frequency is also high, which is why it looks like the green LED is on all the time. Now this capacitor is too small, so I'm going to swap it out and replace it with a 10 microfarad capacitor. Now we can see a more distinct flash from the red LED, though the green LED is still on for most of the time. So the overall frequency is much lower, but the mark to space ratio is still very high. Turning the variable resistor does appear to have some effect on the speed of the flash now as well, so we're making progress. We will come back to this 330 nanofarad capacitor for more tests shortly. Now we've had a little excitement, we need to get back to our objectives and we need to look in detail at the theoretical formulas. Now I want to mention a couple of references I'll be using, and you can look these up yourself, as these contain a lot of detail, but also some contentious information. I'll start with the book by E.A. Parr called IC555 Projects from 1978. On page 12, Parr says the formula for calculating the mark, T1, is 0.7 of RA plus RB times CT, as you can see, which I've highlighted here. There's lots of further information on these pages about what we are looking at in this video, and you can read the theory on these pages as well, which may help you as we progress further. Next, I want to show you the Texas Instruments 555 datasheet, and I've chosen the 2014 edition as it is quite nicely done. And here in the screenshot is the URL, so you can look this up yourself. And on page 11, we see that the formula uses 0.693 of RA plus RB times C to represent the mark time. And you can see all the rest of the formula progressions that we're about to look at as well on that page. So it is clear that E.A. Parr rounded up the constant from 0.693 to 0.7. You might say that's close enough, but if you want some precision, you should use the proper value and not a rounded up value. The terminology they've used is similar, but we'll go with the proper datasheet. So let's now work our way through these formulas and see how they help us. Okay, so looking at the formulas from the datasheet, and we start with the waveform. And this waveform is a square wave, and you can see here that we have a mark, which is the on time, which is represented by TH. That is the time for the high. And then we have the off time, which is the TL, the time for the low or off. So the TH is given by the formula 0.693 of RA plus RB added together times the capacitor value C. And TL, the off time, is given by 0.693 of RB times the capacitor C. And the overall period is given by TH plus TL. So the overall cycle for one full waveform is TH plus TL. That's the period. The overall period is given by 0.693 of RA plus RB times C plus 0.693 of RB times C. So overall, when you do the calculation and you reduce this down, you get 0.693 of RA plus 2RB times C. Now, the duty cycle, or the mark to space ratio, is the ratio of TH to TL. So that's 0.693 of RA plus RB times C in relation to 0.693 of RB times C. And another way to write this is TH over TL. In other words, the mark time over the space time. So that's 0.693 of RA plus RB times C over 0.693 of RB times C. And you can cancel out the 0.693s from the numerator and the denominator, and you can also cancel out the capacitor value from the numerator and the denominator. And that leaves you with the ratio, the mark to space ratio of TH over TL being equal to RA plus RB all over RB. And that means that the value of C is not important in respect of the mark to space ratio. It does have an effect on the overall period and the overall frequency, but it doesn't affect the mark to space ratio. Now, if we want a perfect square wave, and we want to have an equal mark to space ratio, that means TH is equal to TL, then TH over TL needs to be equal to 1. But TH is greater than TL, and therefore it is going to be greater than 1. Now remember that TH over TL is equal to RA plus RB over RB, which means that RB, being in the numerator and the denominator, is going to play a significant factor in the overall mark to space ratio. But also note that because you've got RA in the numerator, then RA plus RB on the numerator is always going to be bigger than just RB on its own on the denominator. Therefore, RA plus RB over RB is always going to be greater than 1. So what values do we choose? Well, RB is on the numerator and the denominator. And if RA is equal to 0, then RB over RB equals 1, i.e. we will have a 1-to-1 mark to space ratio. But RA cannot be equal to 0, but it can tend towards 0. But how low can it go? Conversely, how big can RB be to make RA small enough so that the mark to space ratio tends towards 1-to-1? So let's try some values. So first things first, turn this on. We can see here we've got an asymmetric mark to space ratio. They're not even. This one's on a lot longer than this one. This one's on for a very short period of time, and this one is on for a very long period of time. And just a little issue, it doesn't really matter too much about what I do with this pot here. We're going to be measuring the values of this pot later on. But you can see here that it doesn't make too much of a difference, except at one end. It seems to be that this one is on all the time and this one seems to be off all the time. And we want to know when this one starts flashing. It's just started to flash. I'm going to back it off a little bit more and it stops flashing around about there. So we'll be interesting to see what that value is right there. And as I'm progressing it forward, turning it clockwise, the flashing starts to come back on, and it gets more and more noticeable as I turn it very slowly. So it'd be interesting to see what that position is. But in any case, this issue is not what we really want to look at, because I've got this pot, which is 5 kilo ohms, set up as RB, because it's between pins 6 and 2 here. So this is set up as RB, and I've got over here on 100 kilo ohms set up as RA. So RA is majority in the circuit charging, and RB is in the circuit for charging and discharging. So we've got these the wrong way round, really, or at least how can we put this? We want RB to be a larger value and RA to be a smaller value. So if we want to meet the requirements of that equation, if we want to meet the requirements of this, of tending towards RB over RB equaling 1, then we want RA to tend towards 0, and we want RB to be large in comparison to RA in order for that to be the case here. So here we are, we've said we want RA to tend towards 0. So we're going to swap these over, and that means that RA is going to be the potentiometer at the top, and then RB is going to be this 100 kilo ohm resistor, and we're going to put that between pins 6 and 2. So I'll do that now. So I'm going to remove this from pins 6 and 2, and we're going to put this 100 kilo ohm resistor between pins 6 and 2. It's going in on pin 2, and this is going in on pin 6, like that. And then we'll put this between positive, like that, and pin 7. So this is now RA. So this is now RA, and this is now RB. And you can see just by swapping those two values over, we now have an almost perfect 1-to-1 mark to space ratio on the red and green LEDs. And it doesn't matter how far we turn this, it's fully clockwise now. I'm going to bring it back. It looks like it's a 1-to-1 mark to space ratio. And I'm almost fully anti-clockwise now. Getting there almost. I'll let you know when. There we are. I'm there. That's it. I'm right at the end. I'm just going to back it off now. You can see it's stuck on red. I'm just going to back it off a little bit. And there we are. And it just comes in now. So that's the crucial value. We want to see what that resistor value is. So I'm going to bring in my multimeter. I'll set this to resistance. Can we see that? Just bring it about here. That should be okay. Let's move everything up a little bit like that. I'll set this to ohms. Okay, and what we're going to do is we're going to measure this, the value of this variable resistor. And I'm going to take it out of the circuit in order to do that, so that it's not going to be contaminated. The value is not going to be contaminated by the resistance of the rest of the circuit. So let's see what that value is. And we can see here it's only 240 ohms. So that's pretty interesting, 240 ohms. So we'll make a note of that, around about 240 ohms approximately. Okay, that's very interesting. So RA minimum, we've got one value of 240 ohms. Okay, and RB, oops, typo, RB is equal to 100 kiloohms. So we've got our resistor at 240 ohms. This is going to be RA. So let's plug that back in. That goes to pin 7. That goes to positive. And now we're done with just our little check. So we're going to now swap this capacitor out, which was 10 microfarads. Is that 10 microfarads? Yeah, that's 10 microfarads, so that's coming out. We're going to put back in this 470 nanofarads right here, here and here. You can see it's blinking away like crazy. I need to push this in nice and steadily, like that. So I've not adjusted R1. We now have this quite a high frequency blink. So what we're going to do now is we're going to see the mark to space ratio with this lower value capacitor. We're going to look at it, the waveform, on an oscilloscope. So I'm going to plug in my oscilloscope. So negative to negative here. And then the output is on pin 3, which is the junction of these two little monitoring LEDs. So I'm just going to put that on this resistor point here. Can that clip on there? Yep, I think that's got a hold of that. That's great. And there we are. So I'm just going to adjust the mark to space ratio here. We can see that we've got one cycle of the waveform and it's 10 squares across, and the mark is 5 squares and the space is 5 squares. So that's pretty much a perfect one-to-one mark to space ratio. So it's pretty much spot on. As RA tends to 0, RB becomes the deciding factor in the mark to space ratio. So now we're going to play with this a little bit further. So I'm going to adjust RA. I'm going to adjust RA like this, and I'm going to bring the mark to space ratio back onto the screen, and we can see here now we are 10 squares fully across. I've moved RA to 5 kiloohms, so I've turned it fully clockwise, so it's fully in circuit. So it's a 5 kiloohms in for RA, and RB is 100 kiloohms. So the mark is 5.2 squares, and the space is 4.8 squares across there. So the adjustment here on the times per division, the milliseconds per division, this is the time base. We can adjust that to make it fit on the full 10 squares across, because we're interested in the mark to space ratio. We're not interested in actually calculating what the frequency is at this point. The goal, going back to our objectives, was to look more significantly at getting a 1-to-1 mark to space ratio. And you saw on the screen that we pretty much got that even before we'd worked out what the actual frequency was. We've got the ratio of the resistors comfortable now, which is that this resistor being 5k, round about 5k, or anywhere between, we found 240 ohms and 5k, is very, very low in comparison to this resistor here, which is 100 kilo ohms. So what we're going to do now is we're just going to wind this back. What's going on here? Something's happened with this resistor. Oh, there we are. Is it something here? What's going on here? Oh, there we are. It's that. Just that. That's all it is. Right. So what we're going to do is we're going to wind this back, and we're going to look at the oscilloscope, and we're going to see where it cuts out on the oscilloscope. So I'm just going to wind this back. And we're going to see how low we can take it. I'm just watching the scope. Still watching the scope. Not a great deal of movement. Oh, and there it goes. It's just tripped there. Just going to try and see if we can find the pinch point, exactly where it trips. Whoa! Now that's a weird effect that we have there. We'll come back to that. So it's just... So we're really pushing this 555 now to do weird things. And it doesn't like it. It really doesn't like it. Ooh. And it's gone right there. I'm going to push it back a little bit. Just there. Right, okay. So it's tripped. We're now going to get our meter again. Set this up for ohms. And we are going to measure this resistor again. And it's at around about 75 ohms. Whoa, okay. 75 ohms. Around about 74 ohms. Okay. So we'll write that down. R at 75 ohms trips it. So R A min tripped is 75 ohms. Put that down like that. And then we're going to pan it backwards now, just to restart. We're going to put this back in circuit. So this goes to positive, and this one goes to pin 7. Get that back in there. There we are. And we can see it's absolutely doesn't like that at all. But there we are. That's where it is with a 1-to-1 ratio on the screen. So just adjusting this now, see if I can find it. So at 5k, the resistor is fully in circuit there, it's 5k, and it's 5.2 to 4.8 on the scope. And as I adjust it backwards, it's doing a good job. Let's get that back in there. And right, yeah, it's pretty much 1-to-1 now. Yeah, that's pretty much 1-to-1. So this is where it's a 1-to-1. So let's measure RA, the variable resistor. This is at 1-to-1. So let's just pull these out and see what that value is there. The answer is about 394 ohms, roughly 400 ohms. So for RA min at 21 hertz, the value is around about 400 ohms. Let's call it 400 ohms. Right, so now what we're going to do, now is we're going to look at the ratio of RA and RB and see what the ratio is between the two. So for that, we'll need our trusty calculator again. Back in. There we are. I wonder if you can see that. I hope you can see that. And so RA is 400 ohms and RB is equal to, I think it was 99,400 ohms. Precisely, it's RA plus RB over RB, and we want it to tend towards 1. So let's just see that. RA plus RB over RB. So that's 99400 plus 400. So that's RA plus RB. That's 99,800. So that's RA plus RB over RB, which is equal to 400 plus 99,400 all over 99,400. So that's equal to 99,800 over 99,400 divided by 99,400, and it is, the answer is 1.0040. It is pretty much 1. It's just over 1. So that's it. So that's well, that proves the mark to space ratio is practically 1. It's not exactly 1, and it would never be exactly 1, which means the mark is always slightly bigger than the space by a tiny fraction in this case, and that's because RA is on the numerator, so that makes the mark slightly bigger because RA plus RB is always going to be bigger than RB. So the mark is always going to be slightly bigger. However, the scope screen says something different. And I'm just going to put the scope screen back on. Let's see if we can get this thing back up and running again. What's happened here? Something's happened. What's happened? I crushed it. What have we done? Something stopped working here. Oh, it's because I've got the resistor out of circuit. Let's get that back. Let's get this back in again. Goes to pin 7. It goes to positive. There we go. That's better. The scope screen says that that is a 1-to-1 mark to space ratio. And when we're at the full end of the 5K here, we didn't take that measurement, did we? So that was 5 point. Just looking at it now. It's about 5.2 squares to 4.8 squares. So scope screen, and I'll show you that on the video. Let's put the camera in. So that's 5.2 there and 4.8 there. We do that by positioning the Y rotation like that, and we can see it's just over. It's 0.2 of a square further across there, and this one here is the mark here, and that's 5.2 there. So that's 5.2 there, and that's 4.8 there. Okay, so on the screen we have it looking like this. Oops. And this bit here is 5.2 squares, and this is 4.8 squares. So on the calculator we type in 5.2 divided by 4.8, and we get a mark to space ratio. Mark to space ratio is 1.0833. So this is with the resistor, this resistor here, this resistor here at 5 kiloohms. This is with RA equal to 5,000 ohms. Okay, so what have we learned? We've learned that we can't get a perfect mark to space ratio of 1-to-1, but we can get pretty darn close. So it's imperceptible at low speeds. It's imperceptible to the naked eye when you're flashing 2 LEDs like this very slowly. So if I now put in the big capacitor back in here and put in this big 10 microfarad capacitor in, like that, oops, like that, there we are. The mark to space ratio here is pretty much 1-to-1. You can't tell the difference. You wouldn't see it with the naked eye. You couldn't time it with a stopwatch. It's pretty much 1-to-1. So the theory and the practice line up just about. Okay, going back to our objectives. So we're going to look at these formulas for the mark to space ratios. We've done that. So we did that over here and here. We've asked, can we get a 1-to-1 mark to space ratio? And we pretty much can, but we're going to revisit this in a short while. What are the practical values of R1, R2 and C that are optimal, and are there any limits before the circuit breaks down? Well, we haven't checked what the limit is when the circuit breaks down. So let's look at that next. So we looked at RA, and the minimum we found was 240 ohms, and then we tripped it at 75 ohms, and we thought maybe 240 to 400 ohms is where it what did I put here? 2 hertz. I put 21 hertz. I think I should put I should have put 21 hertz there. But we found that RA min, that is the value of the resistor for RA at which the circuit still operates at a reasonable level, for RA is around about 240 to 400 ohms. It still just about stays intact. In other words, the circuit continues to flash. But what happens when we went below that? That's what we really want to know, what's happening. So let's have a look at that. So we're going to do this again. We're going to turn this down. I think we need to do this with the 330 nanofarads, but we'll get that in a moment. Yeah, that's fine. So I'm just turning this anti-clockwise. Oh, is that? No, that's that. Yeah, that's anti-clockwise. So we're reducing the value here. Still reducing. Ah, and it stopped. Just going to pull it back a bit. There. Right, a bit more slowly this time. And it just goes, it is very, very fine. There is some hysteresis in it. Okay. So let's just have a quick look at that resistor value. So I'll pull this out again. Measure this value here. We're at about 200 ohms. It's jumping around a bit, but it's about 200 ohms there. Oh, it's slower. It's slower. What is it? What is it? This is a bad connection. 110 ohms, 109 ohms. Okay, 109 ohms. Well, we had it at so we had it going all the way down to 109 ohms and it still works. So what I said earlier about roughly 240 to 400 ohms, it goes all the way down to, actually it goes down to about 100 ohms. Very, very low indeed. But then the question is, what happens after that? So why did it trip to be active low? So it went low. In order for that to come on, it would have to be sinking. So it is going low, so it's getting stuck low when we go to too low a resistance. So let's just put that back in. Oops, goes there, and that goes there. Doesn't really matter which way around we put them. There we are. So when I turn this a little bit more anti-clockwise, below that value, just below 100 ohms, 110 ohms, and then here we are, it gets stuck there. So it stops there, and that has gone low. So we just check on the scope, on the oscilloscope. This to here, and 0 is where I'm seeing it now. So I'm just going to calibrate. Right, okay, and oh, shocks! Just broken my thing here. Just put this back together again. I think that's how it goes back together. Yeah, that's it. So this went on here, and that is actually output low. That's fine. That's correct. That's what I said. And can we take this off and put a probe tip? That's it. Ordinary probe tip. And so we can see here that that is low. And well, that's it, I think. There's not really much to see on that. The capacitor is low. So the capacitor is discharged. Yeah. Okay. So that's it. So the 555 dies, it stops and stays stuck low, output low, when this resistor here on pin 7, that's over here, let's move that out of the way. There we are. Whew! I can smell something burning. Whoa, okay, understood. Right, I think we found out what's going on. Haha, right, yes. Well, the variable resistor was burning out there. That was actually smoking. So, so quite an excessive current was passing through that. So that's where we had a little bit of a current flowing. So we had a short circuit current flowing straight from positive to pin 7. So you can't do that. You have to have a resistor there. and that's why it was getting quite a bit steamy in there. Right, so a short circuit between these two pins here, these two wires here, means that the positive is connected not only to pin 8 but also to pin 7, and so that's causing a problem. That causes the 555 chip to hang. There. 2 volts per division. Yeah. 2 volts per division. Stick that in there. That's fine. So, is this chip getting hot? Let's see. Oh, oh! I think that was getting quite hot there. Right. Right, so you can't have pin 7 connected to positive because it shorts the chip out. Right. Oh, that's good. So it was the chip that is shorted. It doesn't like being shorted like that on pin 7. So pin 7 has to have a resistor of more than a few ohms in place. Let's put this back in here. Oh, surprisingly resilient. What a resilient chip. Because even though it's scorching hot to the touch for a few seconds there, removing the short and then immediately putting the resistor back in place, it's just gone back to normal. It's just recovered. Very impressive. Very resilient design. Okay. So are there any limits before the circuit breaks down? Yes, there is. RA must not be equal to 0. RA minimum. Well, a safe value I think we've found is approximately a 1 kilo ohm, and that's on the data sheet, and that's where the data sheet kind of starts. But I've got it down to 200 ohms and 100 ohms round about there, but we can't tell really what was going on inside the chip and how badly it was being affected with such a low resistor. I suppose we could do a calculation and say, well, if we've got a 100 ohms, what's the current that's flowing? So with a 9-volt supply, I is equal to V over R. So 9 divided by 100. And that would have been 90 milliamps. Well, the chip is rated for 200 milliamps, so sourcing and sinking, but not on that input pin there. 90 milliamps, don't know. Maybe it survives that quite comfortably. But when we go down to 0, then that's a short circuit current that's going in there. We don't know how much that is. We don't really want to push it, or do we? Well, I'm not comfortable to push that. Okay, let's try it. So I'll drop that in there like that. Oops, like that. It's pushing 120 milliamps. So it's drawing 120 milliamps at 9 volts. So that's full blast. So that's the short circuit current on pin 7 is 120 milliamps. I'm getting this reading from my power supply. So I've got a voltage of 9 volts and a short circuit current. That's this short circuit here from pin 8 to pin 7 has resulted in a 120 milliamp draw. When I take that out, it drops back down to 0. So that is a 120 milliamp short circuit current. Pin 8 to pin 7. Doesn't like that at all. Okay. Let's write that down. I short circuit on pin 8 to 7 equals 120 milliamps. That's quite a lot. Okay. Right. Let's put this resistor back in. There we are. Very resilient chip. Okay, what we're going to do now is we're going to put back this 330 nanofarad capacitor back in here. Let's push that right in like that. There we are. Okay, I'm going to put this in pin 3. We're back to our one-to-one mark to space ratio, pretty much as we had before. Well, it's 5.2 to 4.8. But now the question is, can we make it better? Can we get it even better? Can we get a perfect one-to-one mark to space ratio? Okay, so how about if we took our chip like this, R555, and we've got pins 4 and 8 like this, and then we have our first resistor comes down like this. This is RA, and it needs to charge the capacitor, and it's going to connect to pins 2 and 6. And then there's the capacitor. Like that. Okay. And it charges through RA only. So how about we charge through RA only, like this, and we have a diode to steer like this. So this is positive. And pin 1 is negative. Whoops. That's, and so the current comes through this resistor, through this diode, and charges this capacitor. And then to discharge, we need to discharge through pin 7. So here's pin 7. And here we want to have a different value resistor, which is the same value as that resistor, and another steering diode. So if we put the resistor here and a steering diode here, like that. There we go, that's a steering diode. Didn't draw it very well, but I hope you can see that. And let's make this 100k and this 100k. Okay, and we'll make these little normal 1N4148s. Like that. So that's what we're going to build now. We're going to build this little steering circuit. This one charges, and then this one discharges. So, yeah, I think that's going to work. Let's give that a try. Right, and we're going to keep the circuit live while we're doing it. Okay, so we've got one resistor here, but it needs to come to a separate point here. So from positive, sorry, that's this one here. I'll take this out. And we need a 100 kilo ohm resistor. I've got to find one. Okay. Right, so from positive, it's going to come to an empty node over here, there like that. And then a diode, a 1N4148 diode. That's okay. Honestly, you need to have a magnifying glass that strong to see these numbers on these tiny components. Especially when you get to my age. Okay, right. So the anode goes to pins 6 and 2, and I need to take this one out of here. So the anode goes to, the anode goes to the 100k here, and the cathode goes to pins 6 and 2, which is over here. That's right. And then the other resistor goes from pins 6 and 2. So that's there. I'm going to take that to another. Oh, blimey. Let me get that around there. I'll take that to. I'll take it from this point here. That's pin 6. Take it out to an empty pin, an empty row, like that. And now the anode of that, which is this end, goes to there, and then that goes to pin 7. Let's see if that works. That does not work. Why that doesn't work. So that doesn't work. So that didn't work. How about like that? So there's 100k there, so it charges up through there like that, shorting out that one on the way down, and then coming out this way. That's pin 7 there. So we'll try that. We'll try that. Okay. So that diode is going into pin 7. This one here we want to remove. So this positive one here goes to the anode of the diode. That's there. And then it goes to positive, which is over here. There you go. And that's actually working there. That's fine. I can get that into there. That's fine. There we are. Right, so let's look at the mark to space ratio on that. And it's about a 2-to-1 duty cycle. Okay. And now hopefully this diode, which goes from the junction of the 2 resistors and that diode with its anode go in here, and then its cathode going to pins 6 and 2, which is over here. Okay, let's see what the duty cycle looks like now. And it works. It works. I think that's working. We have a 5 squares mark and a 5 squares space. It's perfect. Taking up the whole 10 squares of the time base on the screen. And so that is a 1-to-1 mark to space ratio with these 2 steering diodes. So the question is, you would need to have a dual ganged potentiometer and perhaps have a couple of series resistors to set the highest frequency and the lowest resistance, whilst the variable resistor, the dual gang variable resistor, would then determine the span of the frequency range. But unfortunately I don't have any dual gang variable resistors at this point in time. But at least we've figured this out. And I think that is very good. Okay, so we can put this away now, and we can do a final diagram of this. Just turn the scope off. Bring the book back in. So this one here, that works. And we'll just put in a couple of extra resistors here and here, which will be your dual ganged variable resistor. So let's draw the final diagram. And to make a perfect 1:1 mark to space ratio, variable, astable. Using a 555. So it was a resistor like this, and another resistor, then another couple of resistors, which I'll put a little bit further down, and this resistor and this resistor will be preset like this and dual ganged. That means they join together, they spin at the same rate. Oops. I'll bring it back on that. There we are. Okay. And so the minimum value we said here for this resistor here, the top resistor going from positive to pin 7, ideally is something like 1K. But this sets the span anyway, so putting it into this formula here, the 0.693 business over here, to set this period, the mark period and the space period, is determined by the resistor values RA and RB and the capacitor, which was actually 330 nanofarads here, but that could be any value. It's independent of that value. So depending on what frequency you want, you take those two to be RA and then those two to be RB. So this is your RA, and this is RA, and this is RB and RB. well, RA1 and RA2 and RB1 and RB2. In other words, you add them together and you add those two together. But that value and that value are the same, and this is a dual gain resistor, variable resistor, and they're the same. Whew, right. Okay, and then there's the capacitor. Oops. That's the capacitor. That's your positive, that's your negative, yeah. Okay. And then we've got those two diodes. So the first diode goes between the first two resistors, which are here, and it goes to pin 7. So that's from here to pin 7 on the 555. And then the next diode, whoops, I forgot to actually draw the diode in, didn't I? Let's just put that in there. So that's your first diode. And the second diode goes like that. The second diode goes like that. That's a 1N4148, and that's a 1N4148. Okay, and then this goes to pins 6 and 2. And then we can draw the 555 in. Which is 9 volt here and just 0 volt here. And that's where we're at. I think that matches that. So just to go over this one more time. The capacitor C1 here charges by going through RA1 and RA2, so that's the fixed resistor which sets the minimum resistance between positive and pin 7, and RA2, and then goes through this diode here to charge this capacitor. And when this capacitor is charged and it trips the threshold, it discharges through RB1, which is the same value as RA1, and RB2, which is ganged with RA2, and it discharges through that resistor network there and then through this diode here. And because these two values are the same as these two values over here, the capacitor charges this way and then it discharges this way. And that will give you a perfect 1-to-1 mark to space ratio. And I think we can call it a day there. Thanks for watching.